Consider the infinite region S that lies under the curve y equals 1 over x squared. In this section, we are looking at what are called improper integrals. And by improper integrals, we basically mean there's some part of this graph that goes to infinity. So in this example, we're looking at 1 over x squared, and the graph in this quadrant looks like this. Of course, we have the mirror image over here, but we're only considering, in this case, to the right of x equals 1. So if we go all the way to infinity, we know that there is a horizontal asymptote along the x-axis here, and the graph never actually touches there. So most graphs that we've looked at that we want to find the area under the curve, it will have something where either it's a finite area like this, where we're cutting it off at, say, 1 and 4, or we have something where we just are finding the area between the x-intercepts, whatever those might be. But in this case, we're not cutting it off anywhere, and there's nowhere that it crosses the x-axis where we can say here's a good cutoff point. So how do we handle this? Well, let's see what happens. Let's just look at this generic one between 1 and some point out here, t, to the right of 1. So it could be anywhere, but some finite point. So if we integrate this, integrate 1 over x squared, that gives us negative 1 over x. We'll evaluate that from 1 to t. So that gives us negative 1 over t, and then minus a negative 1 over 1, so plus 1, or if we like, we can write 1 minus 1 over t. So, so whatever point t, wherever we want to go out, however far out we want to go, this is 1 minus 1 over t. Now, what happens is we take the limit of t out to infinity. Well, plug in bigger and bigger numbers for t, and that gets 1 over that big number gets smaller and smaller. And so this limit just goes to 1. And so what that tells us is that the area under this curve from 1 out to infinity is 1. And so that's the kind of integrals that we're going to look at as we go along. And there are a couple of there's one other type that we're going to look at, but that's the first one. And so you can see, kind of illustrate, because it seems weird. Anytime you're dealing with infinity, it's hard for your brain at first to kind of understand and make sense of it, because you think there has to be an infinite area under this because we're going out to infinity and we're just adding forever area to this. So why would it not be infinity? But the reality is that it's not. It's not infinite. It is in fact finite, and we can see this. The way this was working out, if we evaluate from 1 to 2, we could evaluate this integral from 1 to 2, and we'd end up with 1 minus a half, which gives us a half. If we go from 1 to 3, it'd end up being 1 minus a third, which is 2/3. And you can see the further out you go, this is getting closer and closer to 1. It's never actually going to get above 1. There's no chance of that. But as far out as you go, you're going to get closer and closer to 1 the farther out you go. Okay, so let's talk about, this is the first type of improper integral. And so a couple of ways to do these. The first way is the way that we saw, where we're going up to it and we're evaluating x from some number out to infinity. And so the way we do this, because you can't really plug in infinity into a function, you can't find f of infinity. The only way to do this is to take the limit as we go out to infinity. So we're going to set this up as the limit as t goes to infinity, the integral from a to t f of x dx. And so we're just going to evaluate this function, the integral of this function, as we have learned before. And then we're going to input the limits, evaluate the limits from a to t. And then once we get that, a is of course just any number, whatever number we want. Then we'll take the limit as t goes to infinity, and that will give us the value of this integral. The other way, of course, if we're going out to negative infinity, we can do the same thing. We'll take the limit as t goes to negative infinity. And then, so now we're starting with the integral from negative infinity to b. So now we're going to go from t up to b, f of x dx. So really the same thing. We're just kind of reversing the direction that we're going, but looking at the same thing. Now, here are a couple of terms. You may have heard these terms before. We're going to see these terms a lot once we get past this chapter on integrals and we get into sequences and series. We're going to introduce it here. So the improper integrals that we just looked at, these two, are called convergent if the limit exists. So if we evaluate this, so like we did in the first example where we ended up with 1, that integral would be called convergent. And then if the limit does not exist, we call it divergent. And so divergent just means that as you take the limit to infinity, you're not going to get a finite answer. So if both of these, here we have the integral from a to infinity of some function, and the integral from negative infinity to a of the same function. If both of these are convergent, then we can define the integral from negative infinity to positive infinity as the integral from negative infinity to a f of x dx plus the integral from a to positive infinity f of x ds. And this is just using the basic rule that, or the property of integrals that you probably saw in Calculus 1, where if you have the integral from a to b of f of x dx, and let's say c is between these two, then you can split the integral up. So you can do the integral from a to c of f plus the integral from c to b of f, and these are going to be equal. So you would have seen that property in Calculus 1. Okay, so let's look at our first real example here. Is the integral convergent or divergent? So we have the integral from 1 to infinity of 1 over x. And so we basically want to follow this process and see, do we get a finite number or do we get infinity? So let's use this. So we're going to use this identity here. So the limit as t goes to infinity, the integral from 1 to t, and we'll look at 1 over x dx. Now we should know that the integral of 1 over x is just going to be ln of x. We'll evaluate that from 1 to t. So we get the limit as t goes to infinity, ln of t minus ln of 1. ln of 1 is just 0, so we'll just leave it like this. So the limit as t goes to infinity of ln of t. Now, hopefully you know the graph of ln, and it looks like that. And so this, as t goes to infinity, so we'll call this the t-axis. As that goes to infinity, ln is also going to infinity. It's going very slowly, but it is going to infinity. So this integral, 1 over x dx, is actually divergent because we do not get a finite answer here. So we would say it is divergent. So let's talk about these two, because this is a little bit interesting, because if you look at the graph of 1 over x and you compare the graph of 1 over x squared, they actually look basically the same. But one of them is finite and converges, and the other is infinite and diverges. So, I mean, we could talk about, you could go in depth on why that is, but we'll just say for our purposes that the 1 over x does not decrease fast enough to slow down the area that you're adding in. So 1 over x squared, you can see it because these are on the same scale. So 1 over x is going to be higher than 1 over x squared. And you can also see that at x equals, say, 10, 1 over x squared. So let's say 1 over x squared would be 1 over 100, whereas 1 over x is just 1 over 10, or 0.01 and 0.1. So 1 over x squared, as long as x is greater than 1 over x squared is always less than 1 over x. And the bigger x gets, the bigger that difference is. Although it's not huge, because obviously we're getting closer to 0. But it is going down fast enough to where this will converge to a finite answer, and this one will not. This one will go off to infinity. So how can you, what kind of rule can we talk about? Well, we can summarize this as follows. The integral from 1 to infinity of 1 over x to the p dx converges if p is greater than 1, and it diverges if p is less than or equal to 1. And of course, if p is negative, this includes the negative numbers, because if p is negative, 1 over x to the p, let's say 1, we'll plug in something for p. Let's say 1 over x to the negative 2. Well, that's the same as x squared. So obviously, if you're looking at the area under this curve as x goes to infinity, this is clearly infinite. So when p is negative, this still applies. And then if p is greater than 1, then we're going to be in this situation. When you get to 1 over x cubed, 1 over x to the 4th, the graph will get smaller even faster than 1 over x squared. So keep that in mind. Of course, you can pretty easily integrate these, but once you get maybe to, well, even if it was a fraction, I mean, you can still integrate those, but that's the rule. So if it's just, does this converge? It's 1 over x to the p. You really just need to look at p. Okay, so that brings us to the second type, type 2. Now, this is where we have some discontinuity, and typically we're talking about a vertical asymptote. So we're discontinuous at b, think vertical asymptote at x equals b, whatever that might be. And so we can write this limit. We can do the same thing. We're going to look at the limit, but now t is not going to infinity. T is going to b. Now, we only need to consider the one-sided limit. So let's say the a is here and b is here. So this graph will look something like this, where we go up to infinity, we have a vertical asymptote there, and so we're finding this area like that. So vertical asymptote, we're just going straight up once we get there, or steeper and steeper, I guess is more accurate. So in this case, we're looking at the left-handed limit. So we're not worried about the two-sided limit, just the left-handed limit as t goes to b, and this will be the integral from a to t f of x dx. So very similar to the other type that we're looking at, is just now instead of the infinity going out horizontally, we're going vertically. And then b, if f is continuous and is discontinuous at a this time, then, so now this is going to be the other side of this picture. So we have the vertical asymptote at A, and now it's going to look something like this. So now we have the right side limit. So x is approaching A from the right. Integral from t to b, f of x dx. Okay, and then of course we can do the same thing if we have discontinuity at c, then we can, and both of these are convergent, then we can just split up this integral, the integral from a to c of f of x dx plus the integral from c to b f of x dx. Okay, so similar ideas as what we were looking at in the first part. Okay, so that brings us to this example. So here we're evaluating from 2 to 5, 1 over square root of x minus 2. And you can see if you plug in 2 here, this function is not continuous at 2 because you get a 0 in the denominator. So this would be an improper integral. So we need the limit as t goes to infinity, or sorry, t goes to 2. And we are coming from the right. So when the lower integral is causing the discontinuity, we got to come from the right. When it's the upper integral, we got to come from the left. And if you forget, you can draw the picture. So you got 2, you got 5, and you don't have to know what this graph looks like, but you know that as x goes to 2, this will be 1 over some small number that's going to go to positive infinity. So you know it's got to look something like this, something like that. You don't know, I guess it's always positive, but that doesn't even matter to us. We're really just worried about how do you remember, is this a left-handed limit or a right-handed limit? So that's really what I'm worried about here. So as x gets to 2, this denominator is going to 0. 1 over a number approaching 0 is going to be going to infinity. And so that's the idea. So we'll evaluate this from t to 5. 1 over square root x minus 2 dx. And if you like, so this is a simple integral, but you might want to rewrite it before you try to integrate. So let's make it x minus 2 to the negative 1/2 dx. And then we'll just add 1 to the exponent, divide. So we don't have any squares, nothing complex here. So we have the limit as t approaches 2 from the right. And we end up with 2 square root x minus 2 evaluated from t to 5. So now just plug in those as you would. So we get, let's do this, we get 2 times square root of 5 minus 2. So that'll be 2 times square root of 3 minus 2 times square root of t minus 2. All right, so now what is this limit? Obviously, this is a constant, so the limit is equal to the constant. When you plug in numbers that are getting closer and closer to 2, and this is continuous until it gets to 2, so you could just plug in 2, but when you plug in 2, that just goes to 0. So this limit is just going to be 2 square root 3. And so says to find this integral, so that's our answer, but if it says does it converge or diverge, then this one converges. All right, so if you have any questions about this, please let me know.